Hey, what's up guys? So here we are back again on the HVAC Optimal Start Math Playground. If you're just joining us, we're studying the mathematics models that optimally start HVAC systems defined in research. So here's the paper. The PNNL paper is the research paper that we're going off of, doing everything in Python. And the basics of this is we're feeding in HVAC data to these math models, and then our ultimate output is minutes required to warm up or cool the zone down before the building starts up. So we've been studying the different models. We're Model 0, Model 1, Model 2, Model 3, and then we're in the Model 4. So a little recap, Model 0 is just a linear degree per minute, kind of simple model that most building automation systems have built in. And then Model 1 is a quadratic regression model that the researchers built. Model 2 is the linear degree per minute. Model 0 plus like this weather ratio, which I'm getting good results using Model 2. Model 3 is also includes outside air temperature, and it's a multiple linear regression model. So we've been studying this the last couple bonus days added to the coursework generated by AI, and we were studying the matrix algebra from scratch. Now we're on to this Model 4, which is a first order response model with some log math defined in here. So yeah, let's kind of look at this a little bit. So we have this alpha A parameter, which is the acceptable deadband temperature tolerance. I actually have that, I use that word as a parameter in my optimal start as well. Alpha B is the initial temperature difference between the zone and set point, and alpha C is this dynamic system response. This is like an iterative model, so it's a little more than just running this couple logarithmic math right here. I think we'll get into that. So we're in the bonus days of the lesson. If you go to lessons, and then we're on bonus day 9. Okay, so we did bonus day 8 yesterday. Let's continue on with day 9 of the bonus section. So the bonus section was just a little bit more context, because this studying these math models were a little bit more than I thought. So we're just getting a little bit more what goes on behind the scenes, which I need. I've been out of university for a good 20 years, so I'm well behind on this, some of this stuff. Also, like when you set up building automation systems, which I was a building automation technician for years and years, you'd never get into deep into the weeds in these math models. This is only for researchers, and then maybe some developers that would work for like building the platform. Maybe they could build this into the blocks that the HVAC programmers use. Or IoT could get deep into the weeds on this stuff too, but we generally wouldn't get into this level if we're setting this up in a real live building automation system. Okay, so here we go, Model 4. Model 4 computes the optimal start time by closing with a closed form log expression from repeated multiplication to exponential. So got some math here, and then we were looking at decay rates earlier. So what if we want an optimal start? We don't need perfect set point. We need close enough. That's deadband. Deadband is typically like the temperature above or below a set point. So if your set point is 70 degrees Fahrenheit and you have a 2-degree deadband, that means 1 degree up and down. So that's what deadband is referring to. So we have an alpha A parameter is acceptable air deadband in degrees Fahrenheit. E0 is the initial air at start time. and C is the decay ratio per sample. So this looks kind of interesting. Take logs to isolate n. Looks kind of a little bit of math going on here. So that's just in Python. So if n is greater than or equal to the log of these different parameters divided by each other. So tiny Python, no NumPy. Let's just see what this does. Let's see, maybe I'll keep this. This was our last math lesson from yesterday. Comment it out. So let's just see how this runs. Python math lesson. So, okay, so this model is just predicting 23 minutes needed. I think it's just to like give us a little bit like what it would be doing in the real world. So it's saying a deadband of 0.5, which would be very low in the real world application. So our initial error is 6 degrees Fahrenheit, and then our decay ratio per minute. So that is kind of interesting. On the linear models, we've been seeing I default to 0.1 degrees Fahrenheit per minute and calculating minutes, which is tuned over time. So it's somewhere right around in there. So this is like, I think, doing the same thing in a decay rate. So which is kind of interesting. Anyways, so like this is calculating minutes from kind of a different way. So like the model 0, we were back calculating minutes from degrees per minute, how off we were from our set point. So this is actually kind of doing something similar, it seems like, but in a different fashion. If C is close to 1, the log C is a small negative number, long time. Interesting. So that's basically our decay rate. If you tighten the deadband from 1 to 0.1, does it go up and down? Okay, so if we increase our deadband, let's increase this by 2.5. So this would be so basically if our set point for the zone was 70 degrees and we had a 2.5 degree deadband, I think that would be up and down. So that would be 68.5, no, it's 67.5 and 72.5. Maybe that I actually might be explaining that wrong. So if we had a set point equals 70 degree F, say degree F, now I'm kind of drawing a blank. Usually like energy code in United States requires a 5 degree deadband. Like that's what by code requirements that they're supposed to set up a building with a 5 degree deadband, but no one ever does that because it's good for energy savings, but it might make some people complain. It'll make the system respond really slowly. Okay, so why am I drawing a blank? So I'm just gonna put this maybe as 4. I think a 4 degree deadband. So if our set point was 72, which is pretty common in the United States, usually you would do like effective heat equals set point minus A, and effective cool would be set point plus A. So we can print effective heat, effective cool, effective heat. So let's just see what that would be. So yeah, 70. Oh yeah, wait, hold up. So actually we do need to divide this by 2. Sorry, I screwed up there for a second. calculation period. So this is pretty common. What I see is that the set point locked in for the tenant is 72. Then with a 4-degree deadband, you get 2 degrees up and down. So like the effective cooling would be 74, and effective heating would be 70, and the control system doesn't do anything if it's within the deadband range, which would be 74 and 70. So now it would be kind of interesting to say, maybe we could build off this. But until then, let's just answer our questions. If you tighten the deadband from, so now if we make it smaller, so we're not really using this here yet, but what if we, so now we're calculating 3 minutes for whatever reason. If our deadband is really small, our model calculates 23 minutes, but now we're calculating 3 minutes. So if we make our deadband smaller, our minutes calculation goes up. Our deadband is a lot smaller. So with a 1-degree deadband, we only get half a degree up and down. That would be a really small deadband, which can make some equipment overshoot and undershoot. Okay, so smaller deadband makes our equation calculate more minutes, which is kind of interesting. If you tighten the deadband, does the time go up or down, and why? Okay, so time goes up. I have to think about that, why that would do that. So it's just the what is C? I think it's just making this top parameter just like a smaller fractional expression, I guess. So that's why it would make the divide, when you divide a bigger number, smaller you get. I don't know. What happens if you accidentally estimate 1.02? So if we have a value less than 1, which we talked about in the last lesson, you're not decaying anymore, you're adding. I think that's kind of obvious. So if we do 1.02, oh wow, so actually we're actually in a negative number here. Interesting. Why is the log C good for system decay? That's a great question. Gosh, it's been so long since I've done math. I'm almost curious now just to do chat with ChatGPT again. Okay, so where are we? So I've used ChatGPT a whole bunch since yesterday even. So we were in, I think here. So on day 9 of the bonus days, the questions. I'm just in days for that first question. If you tighten deadband, that will make the division smaller on the numerator, making it output a larger number. Ultimately, what happens if you accidentally divide this? I saw a negative number, so a number greater than 1, we are no longer decaying, but adding on to. y is the log. Gosh, I'm just gonna say that is the characteristics of using log. Please explain more. Okay, so it's been a little while since we've had some math, so sorry. So this is why we're getting a refresher. Tightening the deadband does time go up or down, and why? Recall Model 4 formula is number of minutes equals log of A divided by the E parameter 0 and the C parameter, which was the decay rate. Tightening the deadband means so this number becomes smaller, which we talked about. That means that becomes more negative. So yeah, time goes up ultimately. When you divide the two numbers, planing it, you're asking the system to get closer to set point, so it must need to run longer while progress slows near the end. That is not a bug. That's exactly how first order systems behave. Makes sense? You need more equipment runtime to get closer to some set point. What happens if you accidentally estimate C equals like that? So yeah, so we're just adding on to. So instead of decreasing by a percentage every step, we're increasing. Makes sense? So yeah, that's how we got the negative number. Why is log C negative for a good decaying system? Yeah, so it's the same concept as that you need to subtract a percentage. You know, each iteration of the step is like you're subtracting 10% and keep subtracting. So Model 4 works only when a system is truly converging, and the tighter your comfort target, the longer convergence takes. Logs appear because first order systems decay multiplicatively, and the negative logarithm of C is the mathematical signature of convergence. Yes, so this is Model 4. It's a iterative convergence model, first order system. So cool. I think that's all for today, guys. So thank you for following along. Maybe we could even sneak peek into bonus day 10. So here we go. We get into some more iterative mathematics, fun stuff. So hope you guys are following along, learning a ton. It's going really slow, so little by little is how we learn things, I guess. So eventually when we get out of these bonus days, I think we pick up right around here somewhere and then get into machine learning models down here. So until then, see you guys tomorrow. Have a good one.